Imagine you're pouring milk into a hot cup of coffee, and in the first few seconds, chaotic swirling lines begin to appear, twisting and curling in a way that's both beautiful and unpredictable. What you're seeing is a phenomenon we call turbulence. What's interesting is that this phenomenon isn't limited to your cup of coffee. It exists everywhere, from the smoke rising from a campfire to the swirling airflow around the wings of a Boeing 747 flying tens of thousands of feet in the air. Physicists described this motion using the Navier-Stokes equations, which were developed in the 19th century by Claude Louis Navier in 1822 and George Stokes in 1845. These equations are now used to design jet engines, submarines, and even to simulate blood flow in the human body. However, we still haven't proven whether these equations always have smooth solutions, and that means that understanding exactly how water flows through a pipe is one of the 7 Millennium Prize problems worth $1 million from the Clay Mathematics Institute. Let's continue with an even simpler experiment. You just need to take a small magnet and bring it close to a metal nail, weighing a few grams lying on the table. Immediately, the nail lifts off the surface, as if the magnet's pull has defeated something much larger. The strange thing is that in that moment, the electromagnetic force from the magnet has actually overcome the gravitational pull of the entire Earth, a planet with a mass of about 5.97 times 10 to 24 kilograms, pulling the nail downward. If you pause for a moment and think about this, it starts to feel unsettling, because measurements in particle physics show that gravity is weaker than the electromagnetic force by about 10 to the 36, a number that's almost impossible to comprehend. This enormous discrepancy is called the hierarchy problem, and it's not a minor detail, but one of the biggest questions in modern theoretical physics. In the Standard Model, we have 4 fundamental forces: the strong force, the weak force, the electromagnetic force, and gravity. But there's no clear reason why one of them should be so much weaker than the others. Some physicists have suggested that we might be missing part of the picture, for example, in string theory, which was developed from the 1970s to the 1980s, where space may have 10 or even 11 dimensions instead of just the 3 we perceive. In those models, gravity might not actually be weak, but simply spread out across additional spatial dimensions, making the part we measure extremely small. But this is where things become uncomfortably familiar, because experiments at CERN, especially the Large Hadron Collider, have still not found any evidence for these extra spatial dimensions. And this brings us back to a rather simple but hard to accept truth. A small experiment with a magnet on your table is actually pointing to a profound gap in our understanding of the fundamental structure of the universe. All of modern physics that we trust is actually built on 2 extremely successful theories that cannot be reconciled with each other. Albert Einstein's general theory of relativity, published in 1915, and quantum mechanics, developed in the 1920s, 1930s, by names such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. If you want a simple way to look at it, general relativity is the theory of the very large, while quantum mechanics is the theory of the very small, and each is extremely accurate within its own domain. General relativity describes how space and time are not a fixed stage, but something that can be curved by mass and energy, like a sheet of fabric dented when you place a heavy object on it. This is not just a beautiful idea. It has been experimentally confirmed, especially when LIGO detected gravitational waves, a faint but clear signal from 2 black holes colliding more than 1 billion light years away. On the other side, quantum mechanics gives you a completely different picture, where particles do not have a definite position until you measure them, where probability replaces certainty, and where calculations in quantum electrodynamics can predict experimental results with an accuracy where the error is only about 1 part in a trillion, or roughly 10 plus 12, a number that, if you stop and think about it for a moment, is almost perfect. So if each theory is correct, you might think that combining them is just a matter of time. But this is exactly where everything starts to fall apart. When physicists try to put these two sets of equations into the same mathematical framework, especially when they try to describe gravity in a quantum way, the results they get are not meaningful. Numbers but infinities, quantities that cannot be measured, cannot be verified, and are essentially meaningless. This is not a small error that can be fixed with a constant or an adjustment. It's a sign that something fundamental is missing in our understanding of the universe. And this problem is not just theoretical, because there are places in the universe where you are forced to use both theories at the same time. Think about a black hole, where a large mass is compressed into an extremely small region of space, creating a point called a singularity, where density becomes infinite and the laws of physics as we know them no longer apply. Or go back in time to the very first moments of the universe, about 1043 seconds after the Big Bang, a tiny period called the Planck time, where the entire universe was compressed into a volume smaller than an atom. And the energy was so high that both quantum mechanics and general relativity had to work together to describe it. In such conditions, the lack of a unified theory is no longer a technical detail, but a major gap in our understanding. That is why physicists have been searching for a theory of quantum gravity for many decades. One of the most famous approaches is string theory, in which fundamental particles are not points, but vibrating strings in a space that may have 10 or 11 dimensions, and different patterns of vibration correspond to different particles. Another approach is loop quantum gravity, which tries to describe space-time as a discrete network rather than a continuous one. These ideas are mathematically beautiful and sometimes intuitively convincing, but so far they all lack the most important thing in science: experimental evidence. No experiment at CERN or any other laboratory has confirmed that any of these theories is correct. And this leads to a conclusion that I always find both fascinating and unsettling. The two most successful theories we have ever built cannot talk to each other, like two completely different languages describing the same reality, but unable to be translated. That means the foundation we use to understand the universe is still incomplete. And if you think about it long enough, you begin to realize that what we know may only be a very small part of a much larger picture. A picture we still don't have the tools to see in full. When we talk about CP, we are referring to two transformations. C is charge conjugation, which means swapping matter with antimatter, turning an electron into a positron and a proton into an antiproton, while P is parity, which means reversing space, as if looking through a mirror, turning left into right and right into left. If you apply both transformations at the same time, you would expect the laws of physics to remain unchanged. For a long time, physicists believed that CP symmetry was a fundamental principle of nature. But that changed in 1964 when James Cronin and Val Fitch conducted an experiment with neutral kaons and discovered that the weak force actually violates CP symmetry, a result so shocking that they received the Nobel Prize in 1980. This showed that nature is not as symmetrical as we once thought, and that, to some extent, matter and antimatter are not treated the same way. But if you stop there, the story is still not strange enough, because when we move to the strong force, the force responsible for holding quarks together inside protons and neutrons, everything becomes suspiciously neat. Within the framework of quantum chromodynamics, or QCD, the equations allow for a parameter called pulse theta, and in principle, the value of theta can be anywhere from 0 to 2 pi. If theta is not 0, the strong force would violate CP symmetry just like the weak force did. But when physicists measure it in experiments, especially through experiments looking for the electric dipole moment of the neutron, they find that if there is any CP violation in the strong force, it must be extremely small, to the point where the theta parameter must be smaller than about 10.10, a number that is almost exactly 0. And this is the part that really bothers me, because there is no clear reason in the theory that forces theta to be this small. It could be 0.1, 1, or even close to pi, but instead it is almost exactly 0 within our measurement precision. This is like having a radio that can be tuned from 0 to 100, but when you turn it on, it always strangely stops exactly at 0, with no mechanisms explaining why. Physicists call this the strong CP problem. And the essence of the problem is not that we don't know the value of theta, but that we don't understand why it is so unreasonably small. Some ideas have been proposed to explain this, such as the Pechi-Quinn mechanism, which suggests there's a new symmetry in nature that automatically pulls theta to 0. And the consequence of this is the existence of a hypothetical particle called the axion. However, despite many experiments like ADMX trying to search for it, we still have no direct evidence for this particle. And so we are stuck in a rather strange situation where our equations allow for a certain level of chaos. But the universe seems to choose an extremely special, almost perfect value without telling us why. If you look back at what we've just discussed, from turbulence that we haven't proven, to the strangely weak gravity, to two theories that cannot be combined, and now a parameter in the strong force that is fine-tuned to an unbelievable degree, you begin to see a pattern emerging. It's not that we can't calculate things, but that there are places where the universe seems to be doing something we don't yet understand. And that, at least for me, is one of the most fascinating yet unsettling feelings in doing physics. One of the most interesting ideas emerged in 1977 when Roberto Peccei and Helen Quinn proposed a new symmetry in nature, now known as the Peccei-Quinn symmetry. Their idea is quite subtle but beautiful in the way of theoretical physics. Instead of accepting that the theta parameter in QCD can be any value and just happens to be close to 0, they assumed there is a hidden symmetry that forces the system to adjust itself so that the effective value of theta naturally approaches 0. If this is correct, then what we call fine-tuning is not a random coincidence, but the inevitable consequence of a deeper structure in the theory. But as is often the case in physics, a mathematically beautiful idea must be paid for by predicting something new in nature. In this case, the consequence of the Peccei-Quinn mechanism is the existence of a completely new particle called the axion, a name taken from a brand of laundry detergent because it was expected to clean up the CP. Problem in the strong force. If axions exist, they would be very light, electrically neutral particles that interact extremely weakly with matter, making them almost invisible to ordinary measuring devices. But it is precisely for this reason that they have become a potential candidate for dark matter, which makes up about 85% of the mass of the universe, but has still not been directly identified. Over the past few decades, many experiments have been designed to search for axions. One of the most prominent is the axion dark matter experiment in the United States, which uses extremely sensitive microwave resonant cavities to try to detect the faint signal that axions might produce when converting into photons in a strong magnetic field. Other experiments such as CAST at CERN or newer projects like HISTAC and MADMAX are also taking part in this search, each targeting different mass and energy ranges, like tuning into a specific frequency across a very wide band. But so far, all we have are increasingly tight limits rather than a confirming discovery. That means if axions exist, they must lie in a parameter range we haven't reached yet, or perhaps they don't exist in the way we imagine. What's interesting is that the axion idea not only solves the strong CP problem, but also opens a bridge between particle physics and cosmology. Because if axions really are dark matter, finding them would solve two major problems at once. But that also increases the pressure to find them experimentally. And so we return to a familiar situation where theory offers a neat and attractive explanation, but nature remains silent, neither confirming nor denying it. This always makes me feel there is a gap between what we think is true and what the universe is actually doing. If axions are discovered tomorrow, it would be one of the greatest discoveries in modern physics. But if they are never found, we will have to go back to the beginning and face the original question again. Why is the theta parameter almost exactly 0? And is there a deeper principle we still haven't seen? And until we have an answer, the strong CP problem remains as a reminder that even in theories we think we understand well, there can be small details that reveal major gaps in our understanding of the universe. If you look at a very ordinary magnet, you will realize something that almost everyone has seen but rarely questions. It always has two poles, a north pole and a south pole. If you cut it in half, you never get a single pole. You only create two smaller magnets, each with its own two poles again. This seems like a basic law of nature, something so obvious that we don't think to doubt it. But in theoretical physics, a very different idea has existed for a long time, and it began with the work of Paul Dirac in 1931. Dirac showed that if there existed a particle carrying a single magnetic charge, a magnetic monopole, then it would explain one of the deepest mysteries in physics. Why electric charge is quantized, meaning why every electric charge in nature always appears as a multiple of a fundamental value. In Dirac's equations, the mere existence of a single monopole somewhere in the universe would automatically require that electric charge be quantized. This turns the monopole from a strange idea into a very powerful explanation for a reality we observe every day. That makes the story much more interesting, because while the equations allow monopoles to exist, and even seem to encourage their existence, in experiments, we have never directly observed a single monopole. For decades, scientists have searched for them in many different ways, from analyzing traces in particle detectors to checking ancient materials that might have trapped monopoles from the early universe. But so far, none have provided confirming evidence. Some models in particle physics, especially grand unified theories, even predict that monopoles should have been produced in large numbers during the very early stages of the Big Bang, when the energy of the universe was extremely high. If that were true, you might expect them to still exist somewhere around us today. But reality shows something completely different. If monopoles exist, they must be extremely rare. Rare to the point that we have never encountered one. This leads to an interesting paradox, because theory seems to say they should exist, while experiment shows they don't seem to be here. One explanation offered is that the inflation process in the early universe, proposed by Alan Guth in 1980, may have stretched space so rapidly that the density of monopoles became extremely low, low enough to be almost impossible to detect in the observable universe. This idea may explain why we don't see monopoles today, but it doesn't actually eliminate their existence. It only pushes them so far away that we cannot reach them. That means we are in a familiar situation. The equations allow something to exist, and even suggest that it should exist, but nature does not provide clear evidence for it. This makes the monopole one of the most interesting ghosts in physics, an entity that can exist in every way mathematics allows, but still hides from every experiment we can perform. If one day we discover a monopole, it would immediately confirm a profound part of electromagnetic theory and particle physics, and could change the way we understand the structure of the fundamental forces. But until that happens, the question remains, very simple but difficult to answer. If the monopole is the key to part of the picture, then where are they? And why are they so hard to find? That question becomes even more unsettling when you look at the cosmological picture. Because if you rewind time to the first moments after the Big Bang, high-energy physics theories show that the conditions at that time were perfectly suitable for producing magnetic monopoles in very large numbers. In grand unified models, when the temperature of the universe reached about 10-15 GeV, just a tiny fraction of a second after the Big Bang, the fundamental forces we know today may have once been unified into a single force. As the universe cooled and these symmetries were broken, special topological structures, such as monopoles, could have appeared as relics from that era. If you stop here, you would expect the universe today to be filled with these monopoles, like remnants left over after a phase transition. And that leads to a very specific prediction. We should be able to detect monopoles in modern experiments, but reality is completely different because we don't see them. And this is precisely what physicists call the monopole problem in cosmology. To resolve this paradox, a very powerful idea was proposed in 1980 by Alan Guth called inflation. in which the universe underwent an extremely rapid expansion phase, lasting only from about 1036 to 1032 seconds after the Big Bang. During this extremely short period, space may have expanded at a terrifying rate, increasing the size of the universe by many orders of magnitude. If monopoles had been created before this phase, their density would have been diluted to nearly zero in the region of the universe we observe today. This idea is very appealing because it not only explains why we don't see monopoles, but also solves many other problems, such as the uniformity of the cosmic microwave background radiation and the nearly flat shape of space. However, like many explanations in theoretical physics, inflation is not a final answer, but a powerful hypothesis, supported by some indirect evidence, but not yet confirmed directly at the level of detail we would like. There are many different inflation models with different scalar fields playing the role of the inflaton, and each model makes slightly different predictions about the structure of the early universe. But so far, we still don't have a single model that has been definitively confirmed. That means using inflation to explain the absence of monopoles is really a reasonable inference, but not entirely certain, like seeing an empty room and assuming someone cleaned it before you walked in. If inflation really happened the way we think, then not finding monopoles today is no longer surprising. But if inflation is wrong or didn't happen that way, then we return to the original question with an even greater sense of unease. Why do the equations predict the existence of monopoles? Why do the initial conditions of the universe seem suitable for creating them, yet we see no sign of them in reality? This is a very typical example of how physics works at the boundary of knowledge, where theory and observation do not fully match, and we have to fill that gap with temporary hypotheses. There is something happening right now that you are completely unaware of. Trillions upon trillions of neutrinos from the sun are passing through your body every second, going straight through your skin, bones, and even the entire Earth, almost without leaving any trace. If you pause for a moment to think about it, you will realize we are living in an invisible rain of particles that our senses cannot detect. The idea of the neutrino was first proposed in 1930 by Wolfgang Pauli when he tried to explain what seemed like a small but very annoying problem in nuclear physics. In beta decay, energy appeared not to be conserved if only the observed particles were accounted for. Pauli suggested that there must be an undetected particle carrying away the missing energy. At first, even he considered it a desperate solution, a ghost particle that he hoped someone would find later. It took more than 2 decades before the neutrino was directly detected for the first time in 1956 by Clyde Cowan and Frederick Raynes, an achievement so difficult that Raynes received the Nobel Prize many years later. The reason neutrinos are so hard to detect is that they barely interact with matter at all. They are only subject to the weak force in gravity, and the probability of a neutrino colliding with an atom is extremely small, so small that you could send a beam of neutrinos through a block of lead several light years thick, and most of them would still pass through without being stopped. This makes neutrinos one of the most transparent particles in the universe. And it is precisely this property that makes studying them extremely difficult, requiring gigantic detectors placed deep underground or underwater to avoid interference from other sources. For many decades, neutrinos were considered a stable part of the physics picture, and in the Standard Model, they were assumed to be massless, traveling at the speed of light, just like photons. This simple assumption helped keep the mathematical structure of the theory neat and consistent. This assumption was not made arbitrarily, but was based on the fact that early experiments did not detect any mass for neutrinos. So the simplest choice was to set it to 0, a reasonable choice that existed for many decades and became part of the foundation of particle physics. During that time, the Standard Model developed into one of the most successful theories we have ever had, accurately describing the behavior of fundamental particles and forces, except gravity, with high precision, and neutrinos seem to be just a quiet component in that system. But if you look more carefully, you will see small signs that the story doesn't quite fit, especially when scientists began measuring the number of neutrinos coming from the sun. Experiments like Homestake in the 1960s, led by Raymond Davis Jr., detected fewer neutrinos than predicted by the solar model, a problem known as the solar neutrino problem. For a long time, it was unclear where the error lay, whether in the solar model or in our understanding of neutrinos. This is the kind of situation physics often faces, where everything seems correct individually but doesn't match when put together. Initially, many suspected that we simply didn't understand the processes in the sun's core well enough. But as experiments became more precise, especially with large detectors like Super Kamiokande in Japan and SNO in Canada at the end of the 20th century, the picture began to change in an unexpected direction. The data showed that neutrinos were not simply disappearing, but were changing from one type to another as they traveled, a phenomenon called neutrino oscillation. And this is where everything started to crack, because if neutrinos can change type, that means they must have mass, even if very small, since in quantum mechanics, such oscillations only occur when the states have different masses. This directly contradicts the basic assumption of the Standard Model that neutrinos are massless. Thus, something that seemed like a minor detail became a sign that our theory was missing an important piece. This is a familiar moment in physics, where a small discrepancy in the data can open a large door. In this case, neutrinos went from being a quiet particle to a clue for new physics beyond what we already knew. What's interesting is that the mass of neutrinos is extremely small, hundreds of thousands of times, smaller than the electron at least. And we still don't know exactly what mechanism produces this mass, because the Higgs mechanism in the Standard Model does not explain it naturally. That means we have a particle that we know exists, we know how to detect, we know it has mass, but we don't understand why it has mass. This is exactly the kind of question physics always leaves at the edge of understanding. So when you think about the neutrinos passing through you right now, you are not only thinking about a strange natural phenomenon, but also clearly seeing a sign that the physics picture we have, no matter how successful, is still incomplete. And there is something deeper that we have not yet grasped. When the Super Kamiokande experiment in Japan, a tank of ultra-pure water containing about 50,000 tons, placed deep underground to avoid interference from cosmic radiation, provided clear evidence that neutrinos did not behave the way we once believed. The research group led by Takaaki Kajita observed that the number of muon neutrinos coming from the atmosphere varied depending on the direction they entered the detector. Specifically, neutrinos that passed through the Earth before reaching the detector were missing compared to those coming straight down from above. The most reasonable explanation for this phenomenon is that the neutrinos had transformed from one type to another during their journey, a phenomenon called neutrino oscillation. This was then independently confirmed by the Sudbury Neutrino Observatory in Canada, led by Arthur B. MacDonald. There, scientists were able to measure the total number of neutrinos from the sun, regardless of their type, and proved that the total number matched the predictions, but the individual types did not, showing that neutrinos were indeed oscillating between different states. These two results not only solved the decades-long solar neutrino problem, but also earned Kajita and MacDonald the Nobel Prize in Physics. More importantly, they forced us to accept something very unsettling. Neutrinos cannot be massless. In quantum mechanics, oscillation only occurs when the corresponding states with different masses overlap, which means that at least two of the three types of neutrinos must have non-zero mass, even if very small. This is the point where the entire neat structure of the Standard Model begins to crack, because in the original version of the theory, neutrinos were assumed to be completely massless, and there was no natural mechanism within that framework to give them such a small mass. What we measure is not the absolute mass of the neutrinos, but the difference in the squared masses between the states. And these values are extremely small, on the order of 10^5 to 10^3 electron volts squared. This implies that the actual mass of the neutrinos is below about 1 electron volt, smaller than the electron by at least 500,000 times. To give you a sense of how small this is, an electron has a mass of about 0.511 MeV, which is hundreds of thousands to millions of times larger than the neutrino. This makes the neutrino one of the lightest particles we know, but paradoxically, this very lightness is a sign of new physics. Several ideas have been proposed to explain this small mass, such as the seesaw mechanism, in which neutrinos may be linked to extremely heavy unobserved particles, pushing their effective mass down very low. But all these ideas go beyond the standard model and require extending the theory. This puts us in a familiar but uncomfortable position where clear experimental data shows that something is true, but our current theory has no place for it. Neutrinos have therefore become a kind of crack in the foundation of particle physics, a small but impossible to ignore sign that the picture we have, although very successful in many areas, is still incomplete. When you connect this with the previous problems, from turbulence that we haven't proven, to the strangely weak gravity, to two theories that cannot be combined, and now a particle that we once thought was massless, but actually has mass, you begin to see a repeating pattern where nature keeps giving us hints that there are deeper layers of reality we have not yet reached. And what always makes me think is that we can no longer say the standard model is the complete picture of particle physics, because neutrinos alone have shown that there is something beyond it. The question is no longer whether there is new physics, but where it lies and how we will find it. This takes us away from the world of individual particles and back to the very early universe, about 3 minutes after the Big Bang, when the temperature was still around 10 Zen 9 Kelvin, and everything was hot enough for nuclear reactions to occur, but cool enough for particles to begin combining stably. During this period, protons and neutrons collided and bound together to form the first light elements, such as hydrogen, helium, and a very small amount of lithium, in a process we call Big Bang nucleosynthesis. This is one of the greatest successes of modern cosmology. The equations describing this process, combining particle physics and thermodynamics, predict that the early universe would contain about 75% hydrogen and 25% helium by mass. And remarkably, these numbers have been confirmed very accurately through astronomical observations, from the light spectra of distant galaxies to the cosmic microwave background radiation. When you look at this agreement, you might feel that we have understood the first minutes of the universe quite well, and for a long time that seemed to be true. But if you look more closely at a much smaller detail, the story begins to get complicated, because the same theory also predicts the amount of lithium-7, an isotope of lithium, and this is where things no longer match. When astronomers observe very old stars, especially population 2 stars, stars formed from nearly primordial material of the universe, they expect their chemical composition to closely reflect what was created in the Big Bang. But what they found is that the amount of lithium-7 is only about 1/3 of the value predicted by theory. This discrepancy is not a small effect or a measurement error, but a significant difference, large enough that it cannot be ignored. This puts us in a familiar but uncomfortable situation, where the same set of equations can predict hydrogen and helium accurately but fails when it comes to lithium. If you are a physicist, you immediately wonder where the problem lies, whether we misunderstood the nuclear reactions during that period, whether some process destroyed lithium after it was created, or even whether some new physics we don't know about was involved. Several hypotheses have been proposed, such as lithium being destroyed inside stars through convection and fusion processes, but current stellar models cannot explain the full extent of the deficit we observe. Other ideas go further, suggesting that strange particles or new interactions may have existed in the early universe, altering the lithium production ratio. But these ideas still lack direct evidence. What makes this problem particularly interesting is that it is not a complete failure of the theory, but a very specific discrepancy in a small detail, like a nearly perfect painting, with one point that doesn't match and cannot be overlooked. And it is precisely such details that are often where new physics appears. When you place the lithium problem next to the previous problems, you begin to see a repeating pattern where our theories work extremely well in many cases, but encounter difficulties at very specific points, and those points may be clues to what we don't yet understand. Therefore, the question, where did the lithium go, is not just a question about a chemical element, but a question about the reliability of the entire story we tell about the origin of the universe. And until we have a clear answer, it remains a reminder that even the parts we think we understand best may hide deeper mysteries. The question, where did the lithium go, sounds simple, but when you really try to pursue it to the end, you will realize that we are facing a real gap in our understanding. And the first reaction of scientists is to look for a normal explanation before thinking about something more exotic. One of the most natural hypotheses is that lithium did not disappear, but has been gradually destroyed over time inside stars. This is based on the fact that lithium is a rather fragile element from a nuclear perspective. It can be broken apart when it is carried down into deeper layers inside a star, where temperatures can reach millions of Kelvin, enough to break lithium nuclei into lighter particles. In many stellar evolution models, convective processes can drag lithium from the surface deeper down, where it is destroyed, and over billions of years, the observed amount of lithium will gradually decrease. It sounds reasonable, and in some cases it does explain part of the phenomenon, but the problem is that this level of destruction is not enough to explain the large deficit we see, especially in population 2 stars, very ancient stars formed from nearly primordial material of the universe, and therefore should quite accurately reflect the initial composition after the Big Bang. When observations show that the amount of lithium in these stars is only about 1/3 of the predicted value, we are forced to admit that stellar interior processes, at least as we currently understand them, cannot explain the entire problem. That leads to a different line of thinking, where physicists begin to suspect that something may have happened right from the early stages of the universe during the Big Bang nucleosynthesis process itself. Some models suggest that new particles may have existed, such as forms of dark matter that interact weakly with light nuclei, altering the rates of nuclear reactions in the first few minutes after the Big Bang. If these particles existed, they could have reduced the amount of lithium produced from the very beginning, causing the predictions of the standard model to be off. This is an appealing idea, because it not only explains the lithium problem, but could also provide clues about the nature of dark matter, which makes up about 85% of the mass of the universe, but has still not been directly identified. However, like many other ideas we have encountered, the biggest issue here is that we do not yet have clear experimental evidence for such interactions. No experiment to date has confirmed that dark matter can influence nuclear reactions in this way, so the hypothesis remains only an unverified possibility. Another approach is to re-examine the nuclear reactions in the Big Bang nucleosynthesis model itself, because the reaction rates between protons, neutrons, and light nuclei are measured in the laboratory and then fed into the cosmological model. If there are errors in these measurements, or if the conditions in the early universe differed subtly from what we can recreate in the laboratory, then the prediction for lithium could be wrong. But the problem here is that these reactions have been studied very carefully for many decades. And although there are always uncertainties, they are not large enough to explain the discrepancy we see. When you put all these possibilities together, you begin to see something familiar in modern physics. No explanation is entirely satisfactory, and each direction solves only part of the problem while opening up new questions. This is exactly the state science often finds itself in when facing a real mystery, where current models begin to show small but clear cracks. What makes the lithium problem special is that it occurs in a theory we have great confidence in, because Big Bang nucleosynthesis not only explains lithium but also explains hydrogen and helium very accurately. Therefore, you cannot simply reject the entire theory just because of one discrepancy. Instead, you have to accept that there is some detail we do not yet understand, a missing piece in the picture. When you look more broadly, you will see that the lithium problem does not stand alone, but is part of a series of signs indicating that current physics is incomplete. From the mass of neutrinos, to the absence of monopoles, to deeper issues such as the incompatibility between quantum mechanics and general relativity. And what always makes me think is that small discrepancies like this are often not errors, but hints, clues that nature leaves behind to lead us to deeper theories. So when you ask, where did the lithium go? You are really asking a much larger question. Whether the story we tell about the origin of the universe is complete or not, or whether we are still missing an important part that has only begun to reveal itself through these seemingly small details. The proton is a fundamental component of the atomic nucleus, carrying a positive electric charge and determining the identity of the element. According to everything we observe, it appears to exist forever, unchanging and not decaying, at least in every experiment we have ever performed. But when physicists began building deeper theories aimed at unifying the fundamental forces, especially the grand unified theories, or GUTS, a completely different picture emerged. In these theories, the strong, weak, and electromagnetic forces are unified into a single force at extremely high energies, around 1015 to 1016 GeV. And in that process, particles we thought were stable, like the proton, can actually decay through rare interactions. This means the proton is not immortal, but has an extremely long lifetime, possibly up to 1031, 1034 years, or even longer. Numbers so large they far exceed the current age of the universe, about 13.8 billion years. If you think about that, it starts to change the way you view matter, because it says that everything around you, from rocks and water to the human body, is not permanent, but only temporary on a sufficiently large time scale. In many GUT models, the proton can decay into light matter particles, such as a positron and a pion. And although the probability of each event is extremely small, if you have a large enough number of protons, for example, in a large block of matter, you can hope to observe a few decay events over a sufficiently long time. This has driven scientists to build gigantic experiments to search for proton decay, because detecting such an event would be direct evidence for grand unified theories and would provide a profound insight into the fundamental structure of matter. But at the same time, it also raises a very basic question. If the proton really decays, that means matter cannot exist forever, and in an extremely distant future, all atoms will disintegrate, leaving behind a universe completely different from what we see today. This is not just a technical detail in particle physics, but also a statement about the ultimate fate of the universe, where all material structures will gradually disappear over time. However, like many other issues we have discussed, the story does not stop at theory, because so far we have never observed a single proton decay. Large experiments like Super Kamiokande, with tens of thousands of tons of pure water and extremely sensitive sensors, have been monitoring for many decades without detecting any such event. And this has pushed the lower limit on the proton's lifetime higher and higher. That puts us in a familiar situation where theory predicts something important, but experiment has not yet confirmed it. Each time we do not see a proton decay, we not only learn that it lives longer than we thought, but also have to adjust our theoretical models. Some simpler versions of GUTS have been ruled out precisely because they predicted proton decay faster than what we observe, while more complex models still survive, but with parameters adjusted to fit the data. This makes the proton one of the most interesting particles in physics, not because it is complicated, but because it lies at the boundary between what we think is permanent and what may change. When you ask whether the proton is truly immortal or not, you are not only asking about a specific particle, but touching on a larger question about the nature of matter and time. And the answer, at least for now, is that we do not know for sure. And it is precisely this uncertainty that makes the issue both fascinating and unsettling. The only way to answer that question is not to rely on speculation, but to look for direct evidence. And that is exactly why physicists have built gigantic experiments to observe a phenomenon that may occur extremely rarely, most notably Super Kamiokande in Japan. This device is unlike any ordinary laboratory. It is a gigantic cylindrical tank containing about 50,000 tons of ultra-pure water, placed more than 1,000 meters underground in the Kamioka mine to avoid interference from cosmic rays. Surrounding the tank are thousands of extremely sensitive optical sensors that can detect very faint flashes of light produced when a charged particle moves through water at high speed. The idea here is quite simple but very subtle. If a proton in a water molecule suddenly decays, it will produce secondary particles, such as a positron and a pion, and these particles will create Cherenkov light as they travel through the water, leaving a characteristic signature that the sensors can record. By monitoring a gigantic number of protons, about 1034 protons in the entire volume of water over a very long time, scientists hope that even though the decay probability of each individual proton is extremely small, a few events will still occur that we can observe. This experiment has become one of the most important tools in the search for proton decay, as well as in the study of neutrinos. But after decades of observation, the result has been a remarkable silence. No proton has been confirmed to have decayed. This does not mean the proton is definitely immortal, but only that if it does decay, its lifetime must be longer than what we can observe within the operating time of the experiment. From current data, physicists estimate that the proton's lifetime must be greater than about 1034 years for some common decay channels, a number so large that if you compare it with the age of the universe, about 1.38 times 10 years, the proton lives longer than the universe by at least 1,000,000 trillion times. This number is not only impressive, but also creates enormous pressure on grand unified theories, because many early models predicted proton decay with much shorter lifetimes and were therefore ruled out when experimental data found no corresponding signal. Theorists have had to adjust or rebuild their models to fit the new limits, often by pushing the unification energy higher or introducing mechanisms that reduce the decay probability. This creates a situation that feels familiar in a somewhat unsettling way. Every time we do not see a proton decay, we not only obtain a new number, but also have to change the way we think about fundamental theories. And although the failure to detect proton decay is not a failure of the experiment, because it provides important information about the limits of the phenomenon, it still leaves an open question. Does the proton actually decay, but too rarely for us to observe? Or is there some deeper principle protecting its stability that we do not yet understand? When you place this next to the previous problems, you begin to see a repeating pattern where our theories often predict very specific phenomena, but nature does not always confirm them in the way we expect. That does not mean the theories are completely wrong, but that they may be incomplete, and each non-detection result is actually an important piece of data that forces us to rethink. Therefore, the search for proton decay is not only about waiting for a rare signal, but also a continuous test of how we understand the fundamental structure of matter. And until we have a clear answer, the silence from experiments like Super Kamiokande remains part of the story, and part no less important than any discovery we hope to see. Imagine you fire particles, such as electrons, through a barrier with two narrow slits and a screen behind it to record where they land. If you think in classical terms, you would expect each electron to pass through one of the two slits and create two bands on the screen, corresponding to those two paths. But when physicists performed this experiment, they got a completely different result. Instead of two bands, they saw an interference pattern with many alternating bright and dark fringes, just like what you see when water waves overlap. This showed that electrons, which were thought to be particles, behave like waves when not observed. What is even stranger is that you can fire electrons one at a time, individual particles, And over time, the interference pattern still appears, as if each electron somehow knows about the existence of both slits and interferes with itself. This result has been confirmed through countless experiments since the 1920s, with increasingly sophisticated variations, from electrons to neutrons and even large molecules. Each time it is repeated, nature gives the same answer. At the microscopic level, particles do not behave like solid objects with definite trajectories, but like probability waves spreading through space. But this is where things become truly puzzling, because if you place a measuring device to determine which slit the electron goes through, the interference pattern disappears, and instead you see exactly two bands as predicted by classical physics, as if the electron suddenly decides to behave like a particle with a definite path. This is not a small effect or a measurement error, but a complete change in the system's behavior simply because you performed a measurement. You might try to explain this by saying the measuring device disturbs the electron. But even when scientists design sophisticated experiments to minimize interference, the result remains the same. The act of measurement in some way changes the outcome. This is what we call the measurement problem in quantum mechanics. And it is not just a technical question, but a question about the nature of reality itself. In the mathematical description, the state of the electron is represented by a wave function that spreads out and contains all possibilities. And when you measure, this wave function seems to collapse into a specific result. But what the theory does not clearly state is what this collapse process really is and why it happens. There are many different interpretations. From the Copenhagen interpretation that says collapse is a fundamental part of nature, to ideas like decoherence, where the system interacts with the environment and loses its interference. But none of these explanations is fully accepted, and none has been definitively confirmed by experiment. What makes this problem special is that it does not lie at the edge of physics, but at its very center, because quantum mechanics is the foundation for everything from chemistry to semiconductor technology, and we use it every day without needing to fully resolve this issue. That means we have a theory that works extremely well for predictions, but does not clearly understand its deeper meaning. And if you think about it long enough, it starts to become unsettling in a very different way from the previous problems. Before, we could say we lacked data or a unified theory, but here we have both data and theory, and still there is no clear answer to the basic question: why does measurement change the result? When you ask this question, you are not only asking about a specific experiment, but touching on a much deeper issue about the role of the observer in physics, about whether reality exists independently of our observation of it. And that is a type of question that traditional physics is not accustomed to handling. Therefore, the double-slit experiment, even though simple enough to be explained in a basic classroom, contains one of the deepest mysteries of modern science. And it shows that even when we have extremely powerful mathematical tools, there are still questions we do not know how to answer. Not because they are too complicated, but because they touch the very foundation of how we understand the world. When you say that measurement changes the result, you are forced to ask exactly what is happening in that process. And one of the oldest interpretations is the so-called Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. According to this view, the wave function describes all the possibilities of the system, and when you perform a measurement, the wave function collapses into a specific state. That means before the measurement, the electron does not have a definite position, but exists in a superposition of possibilities. And the measurement is what selects one of those possibilities. This is a very pragmatic interpretation because it allows you to calculate and predict experimental results accurately. But if you ask, what exactly is this collapse, or how does it happen? The answer becomes vague, almost avoiding the question rather than explaining it. Some physicists accept this as part of nature, that at a fundamental level, reality does not have definite values until it is measured. But for many others, this is not satisfying enough, because it seems to assign a special role to the act of measurement without a clear mechanism. It was precisely from this dissatisfaction that a completely different interpretation was proposed in 1957 by Hugh Everett III, commonly known as the many worlds interpretation. In this view, there is no collapse of the wave function. Instead, all possibilities occur, but in different branches of the universe. That means when you perform a measurement, the universe splits into multiple versions, each containing a different outcome, and you only experience one of them. This is an extremely bold idea because it eliminates the need for an undefined collapse process. But in return, it requires you to accept the existence of an almost infinite number of parallel universes that we cannot directly observe. There are other interpretations as well, such as decoherence, which tries to explain the loss of interference by considering the interaction between the system and its environment, or hidden variable models. But all of them share one common problem. None of them has been definitively verified by experiment. These interpretations all make the same predictions about experimental results, and therefore you cannot design a simple experiment to distinguish between them, at least with current technology. This puts us in a very different situation compared to the previous problems, where we lacked data or lacked theory. Here, we have both data and a mathematical theory that works perfectly, but we still do not have a clear answer to the question, what does that mean? When you think about this, you begin to see that the question is no longer just about electrons or photons, but about the nature of reality itself. Because if a particle does not have a definite position until it is measured, what does that mean for the world we experience every day? Does reality exist independently of our observation of it, or is what we call real only the result of the interaction between the system and the observer? This is a kind of question that classical physics never had to face, because in Newtonian mechanics, objects always have definite position and velocity, whether anyone is looking or not. But in quantum mechanics, we are forced to consider the possibility that reality at the fundamental level is not definite in the way our intuition expects. This does not mean that the world around you disappears when you are not looking at it, but rather that the deepest description we have of microscopic systems does not fully match the way we think about reality at large scales. What makes this problem special is that it is not a small error that can be fixed with a constant or an adjustment, but a gap in the way we interpret the very theory we use every day. And so, when you return to the double-slit experiment and ask why measurement changes the result, you are not only asking about a physical phenomenon, but touching on a much deeper question. How well do we really understand reality? Up to now, the most honest answer we can give is that we can describe it, we can predict it with astonishing accuracy, but we do not yet truly understand it, in the sense that we understand other phenomena. And that is one of the reasons why quantum mechanics is both the greatest success and the deepest mystery of modern physics. When you write down the physics equations that describe the world, you will realize that they not only contain mathematical structure, but also fundamental constants, numbers that you cannot derive from theory, but must measure from experiment. If you list them, you will find there are about 24 or more than 24 such constants, often cited as around 26 in the framework of the extended standard model. These include the masses of fundamental particles, the coupling constants of the strong, weak, and electromagnetic forces, the neutrino mixing angle, as well as cosmological parameters, such as the cosmological constant. These numbers do not come from any deeper principle that we know. They are simply values that nature chose, and we measure them through experiments with ever-increasing precision. For example, the fine structure constant, often denoted as alpha, has a value of about 1/137. A number that appears in every calculation involving electromagnetism, from atomic structure to the light spectra of elements. The gravitational constant, G, determines the strength of gravity, while the cosmological constant, Li, is related to the accelerated expansion of the universe. What is remarkable is that these constants are not arbitrary numbers in the sense that they could take any value without affecting the structure of the world. Because when physicists begin to change them in theoretical models, they discover that even a very small change can lead to a completely different universe, one that might not even be able to exist in the way we understand. If the electromagnetic force were a little stronger, electrons would be held more tightly to the nucleus, completely changing chemistry. If weaker, atoms might not be stable. If the strong force changed by just a few percent, atomic nuclei might not form. Or conversely, everything might collapse into heavier structures without the diversity necessary for chemistry. If the cosmological constant were a little larger, the universe would expand too quickly for galaxies to form. If smaller or negative, the universe might collapse before life had a chance to appear. These examples are not vague speculation, but are based on specific physical models. And when you look at the entire set of these constants, you begin to see something strange. They seem to lie within a very narrow region of parameter space that allows the existence of complex structures, from atoms to stars and galaxies. This is often called the fine-tuning problem, because the values of the constants appear to be fine-tuned to a very specific degree, as if they had to fall within that range for the universe to exist in the way we observe. What makes this problem unsettling in a different way from the previous ones is that it is not a direct contradiction between theory and experiment, but a question about the origin of the parameters in the theory itself. In the earlier sections, we saw cases where theory did not match data or was missing a component. But here, the theory works well with the given values. The problem is that we do not know why those values are what they are. You can imagine that if you were given an equation and had to choose the numbers in it to create a stable and rich world, you would have to choose very carefully. And that seems similar to what we see in nature. This leads to a very simple but difficult to answer question. Why do the fundamental constants of the universe have the values they do instead of other values? This is not a question you can answer just by measuring more precisely, because no matter how many decimal places you measure, you still only have a number. And the question why that number remains. When you ask this question, you begin to step outside the safe zone of experimental physics and enter a region where our current theory does not provide a clear answer. Some physicists hope that a deeper theory, such as a complete version of string theory or a final unified theory, might derive these constants from fundamental principles, turning them from arbitrary numbers into inevitable results. But so far, we do not have such a confirmed theory, and therefore these constants remain as basic facts that we must accept. When you look at this together with the previous problems, you begin to see a repeating pattern at a deeper level. It is not only that we lack answers for some phenomena, but that we may not yet understand how the questions should even be asked in the first place. And that leads to a feeling that I think is familiar if you do physics long enough, that you can calculate very precisely what will happen if you know the constants, but you do not know why the universe chose exactly those constants. And that is a gap we still do not know how to fill. If you calculate its value from quantum field theory by adding up the energy contributions from the quantum fluctuations of the vacuum, you will get a number that is about 120 times larger than the observed value, a discrepancy that many consider the largest between theory and experiment in all of physics. To help you visualize, this is not off by a factor of 2 or 10, but by a number with 120 zeros, a gap that is almost impossible to imagine. And for the actual value of Li to be as small as we measure, all the large contributions in the theory must cancel each other out with nearly perfect precision, like taking two gigantic numbers and having them cancel each other to 120 decimal places. This is not a minor detail, but a sign that there is something very deep that we do not yet understand about the structure of the theory. When you move away from the cosmological constant and look at the fundamental forces, the story is no less remarkable. If you change the strength of the strong force, the force that holds quarks together inside protons and neutrons, by only about 2%. Calculations show that the atomic nuclei we know as stable would no longer exist. Either they could not form, or they would become too stable and not allow the nuclear reactions necessary to create diverse elements. That means chemistry, and therefore biology, could not exist in such a universe. If you turn to gravity and imagine it were a little weaker than its current value, the expansion of the universe after the Big Bang might be too fast for matter to clump together into galaxies and stars, and you would have a dilute, almost empty universe where no large structures form. If gravity were stronger, the universe might collapse quickly or form structures that are too dense, unsuitable for the long-term existence of stable star systems. These examples show that the constants do not just lie within a reasonable range, but actually lie within an extremely narrow region that allows the existence of the complex structures we observe. When you combine all of this, you begin to see a picture in which the parameters of the universe appear to have been chosen with extremely high precision. And that leads to an unsettling question. Could this possibly be the result of chance? In a vast parameter space where constants can take many different values, the probability that all of them simultaneously fall within the narrow range suitable for the existence of a universe like ours seems extremely small. And that makes many people feel that something here needs to be explained. However, it is important to be careful, because saying that something could not happen by chance often depends on how you define the space of possibilities and how you evaluate probability. And in the case of the universe, we do not have a complete theory to do that accurately. Nevertheless, the sense that there is a remarkable degree of fine-tuning still remains, and it does not disappear when you dig deeper into the details. Some physicists see this as a sign that there may be a deeper principle, some mechanism that forces the constants to take specific values, while others argue that this may be the result of us only observing universes, where the constants allow the existence of observers, an idea often called the anthropic principle. But before going to those explanations, what we can honestly say is that the level of precision we see in the fundamental constants is very remarkable, and they pose one of the deepest questions in modern physics. When you look back at the entire chain of problems we have gone through, from turbulence that we haven't proven, to neutrinos having mass, to the incompatibility between theories, and now to numbers that seem to have been chosen with extremely high precision, you begin to see that the gaps in our understanding are not only in specific phenomena, but also in the very parameters that define the universe. And that makes fine-tuning not just a technical problem, but one of the greatest mysteries, because it touches on the question of why the universe has the properties it does, instead of a completely different set. And until we have a clear answer, that question will remain there, as a reminder that we may still not understand the deep principles governing reality. Those fine-tuned numbers force us to confront explanations that go beyond what traditional physics usually accepts. And one of the most prominent ideas is the possibility that the universe we observe is only a very small part of a much larger set, what physicists call the multiverse. In this view, the fundamental constants do not need to be uniquely determined by a single theory, but can take different values in different universes. And we simply happen to be in a universe where those values fall within the range that allows complex structures to exist. This idea did not come out of nowhere, but originates from specific theories, especially inflationary models in cosmology and developments in string theory. In some versions of inflation, the rapid expansion of the universe does not happen only once, but can continue in different regions of space, creating separate bubbles of universes, each of which can have different initial conditions and even different physical constants. This is often called eternal inflation, a scenario in which the universe is not only large, but also gives birth to many different regions with different properties. In string theory, the picture is even more complex, because the theory allows for a gigantic number of different configurations of higher dimension space, often called the landscape, with an estimated number that may reach 10^500 possibilities, each corresponding to a different set of physical constants. If you combine these two ideas, you have a theoretical framework in which it is not surprising that constants can take many values, and the question why this value is replaced by which region of the multiverse are we in. This has a certain appeal because it can explain fine-tuning without needing a specific fine-tuning mechanism. But it also raises another problem: how to verify such an idea. So far, we have no direct evidence for the existence of other universes, and by definition, the multiverse may lie beyond our observational capabilities, at least with current tools. Some proposals try to find indirect signs, such as collisions between bubble universes that might leave traces in the cosmic microwave background radiation, but so far none have been widely accepted as definitive evidence. This makes the multiverse a controversial idea because it lies at the boundary between physics and philosophy. It may explain some phenomena, but it is difficult to verify in the way experimental science requires. Along with the multiverse, there are even more far-reaching lines of thought, such as the hypothesis that our universe might be a kind of simulation. A simulation created by some computational system. This idea does not come directly from physics, but from philosophy and computer science. Yet some people see it as a way to explain why the laws of the universe have such clear mathematical form and why the constants have their specific values. However, like the multiverse, the simulation hypothesis faces the same basic problem: lack of verifiable evidence. You can build logical arguments in its favor, but it is very difficult to design an experiment that could distinguish between a real universe and a simulated universe in the sense that we understand. When you place all these ideas next to each other, you begin to see that they are not definite answers, but different ways to confront the same question. Why do the constants of the universe have the values they do? What is important is to recognize that although these ideas may be appealing and sometimes very creative, they have not yet been confirmed in the way other physical theories have been verified. That does not mean they are wrong, but only that we are in a region where evidence is still lacking. If you look back at the entire journey from the beginning, from very specific phenomena like turbulence and neutrinos, to the broad questions about the structure of the universe, you will see a repeating pattern. We have very powerful theories that allow us to describe and predict many phenomena. But when we reach the deepest questions, we often have to face gaps in our understanding. And in the case of fine-tuning, that gap leads us to ideas like the multiverse or simulation, not because we have proven them, but because they are reasonable ways to think about the problem when there is no clear answer yet. The most honest thing we can say at this point is that we do not know why the constants of the universe have the values they do. And although we have promising directions, we still do not have a definite answer. And perhaps that is not a weakness of science, but a sign that we are standing at the boundary of what we can understand, a place where the questions are sometimes more important than the answers. Looking back at all the problems we have just gone through is not about feeling that there are too many things left unexplained, but about understanding the true meaning of that fact. Because it is very easy to fall into the thought that these are failures of science, that if we truly understood the universe, such questions would not exist. But that view misses a core point about how science actually works. Problems like turbulence that has not been fully proven, the enormous discrepancy between the fundamental forces, the incompatibility between quantum mechanics and general relativity, neutrinos having mass when they shouldn't, the lithium deficit compared to predictions, protons that may decay but have never been observed, or the constants that appear to be fine-tuned with extremely high precision. All of these are not signs that science is failing. On the contrary, they are signs that science has reached the boundary of current understanding. If you look at the history of physics, you will see that every major advance began with a mismatch, a small detail that the current theory could not fully explain. And it was precisely those mismatches that forced us to rethink our foundational assumptions. Newton's classical mechanics once described the motion of objects with astonishing accuracy, but it could not explain the anomalous orbit of Mercury. From that small discrepancy, general relativity was born, completely changing the way we understand space and time. Maxwell's equations described electromagnetism beautifully and consistently, but when applied to microscopic phenomena, they no longer fit. From that contradiction, quantum mechanics was developed, bringing an entirely new view of reality. This shows a familiar pattern. The cracks in a theory are not signs of weakness, but the places where progress begins. When you look at the current problems in this way, you begin to see them not as obstacles, but as clues. Signals from nature indicating that there is a deeper layer of reality we have not yet understood. Another important point is that science never aims to provide final and unchanging answers, but rather to build increasingly better models to describe the world. Every model has its own domain of applicability. When you use a theory within the range where it has been tested, it can be extremely accurate. But when you push it beyond that range, you begin to see its limits, and it is precisely those limits that tell you where the theory needs to be expanded or replaced. This is why understanding the limits of a theory is just as important as applying it, because if you do not know where it stops, you will not know when you are stepping into unexplored territory. In science, saying we do not know is not an admission of failure, but a necessary step forward. Because only when you realize there is something you do not understand do you gain the motivation to explore it. If you pretend you already have the answer, you close off the possibility of asking new questions. And it is those questions that are the source of every discovery. When you look at problems like the measurement problem, you see that they are not just technical questions, but challenges to the way we understand reality at a fundamental level. And we may need entirely new concepts to describe those phenomena. When you look at fine-tuning, you see that the question is no longer what happens, but why were the initial conditions like that? A type of question that traditional physics does not yet have the tools to answer. This does not mean those questions cannot be solved. It only means we do not yet have the right approach. Another aspect of science that is often overlooked is that it is not just a collection of correct results, but a continuous process of correction, where each generation of scientists not only builds upon the work of those who came before, but also corrects, expands, and sometimes replaces it. This means scientific progress is not a straight line, but a series of adjustments, where each small discrepancy in the data can lead to a major change in theory. When you put all of this together, you begin to see that the problems we have discussed are not exceptions, but a natural part of the scientific process. They show that we are in a stage where current theories have reached a very high level of accuracy in many areas, but at the same time are reaching their limits, and that creates opportunities for the next major advances. If you think about it differently, you could say we are living in a very interesting time, where we know enough to recognize what we do not know, but not enough to fill those gaps. This creates a state that is both stable and unstable, where current theories still work well, but are no longer sufficient to answer all questions. And it is precisely that state where science thrives the most, because it forces us to rethink our basic assumptions and search for new ideas. When you look back at everything we have said, you can see a common theme running throughout. The universe does not simply obey our intuition, and every time we think we have understood it, it shows us a detail that makes us rethink. That does not make science weaker. On the contrary, it makes science stronger, because it forces us to be honest about what we know and what we do not know. And perhaps this is the most important point. The essence of science does not lie in having all the answers, but in the ability to ask the right questions and pursue them persistently. Once you accept that, the mysteries we have discussed no longer feel like problems that need to be solved immediately, but become directions, pathways leading to deeper understanding. And if you look at it that way, you will see that not having all the answers is not a weakness, but an essential part of the process of discovery. Because if everything were already clear, there would be nothing left to discover. What makes science special is not that it can answer every question, but that it provides a way to get closer to the answers, step by step, through observation, experimentation, and the willingness to change our views when necessary. And in that context, the problems we have discussed are not endpoints, but signs that we are still on the journey, a journey where each new question opens up a small part of a much larger picture. So when you look at these mysteries, you may feel that there is so much we do not know, but you can also see that it is precisely that which makes science alive, because it means there are still great discoveries ahead. And if there is one thing all these problems teach us, it is that understanding our own limits is more important than pretending we have none, because only when you know where you are can you find the way to go further. And the ability to recognize those limits is one of science's greatest strengths. I have always liked questions more than answers, not because answers are not important, but because answers often bring a sense of closure, while questions open up a direction. When you have an answer, you tend to stop, feeling that you have understood. But when you have a good question, it forces you to keep thinking, keep checking, keep doubting. And in science, it is precisely that state that has value, not certainty, but the continuous process of moving closer to the truth. I have never felt comfortable with answers that sound complete but cannot be verified, because in physics, an idea only has real value when you can put it in front of experiment and let nature decide. This leads to what I consider the most important principle: intellectual honesty. That honesty is not just about telling the truth to others, but more importantly, about not deceiving yourself. You must always ask yourself, do I really understand this? Or am I just repeating what I have heard? You must be willing to say, I don't know when necessary, even when it is not easy. Because in science, pretending to understand is one of the most dangerous mistakes. Once you believe you understand something when you actually do not, you stop asking questions. And when you stop asking questions, you stop making progress. That is why doubt is not an obstacle, but a tool. When you doubt a result, you check it again. You find other ways to confirm or refute it, and through that process, you understand it more deeply. If you do not doubt, you accept everything as it is, and science stops there. What is interesting is that doubt does not mean you believe in nothing. It means you are always ready to test your beliefs against the data. This is especially important when you face problems like the ones we just discussed, where current theories work very well in many cases, but encounter difficulties at very specific points. In those situations, the easiest thing to do is to try to defend the theory by adjusting small details. But what is more important is to ask whether there is something deeper we are missing. That requires honesty, because you must be willing to accept that what you thought was correct may not yet be complete. Another aspect I have always found important is how we view not knowing. In many fields, not knowing is seen as a weakness, something that needs to be hidden. But in science, not knowing is the starting point. When you say, I don't know, you are opening up space for exploration. You are acknowledging that there is something beyond your current understanding. That very acknowledgement allows you to go further. If you pretend you already have the answer, you close off the possibility of learning because you are no longer searching. This may sound simple, but in practice it is very difficult, because humans have a tendency to want to feel certain and to have clear answers. But science does not work that way. It does not provide absolute certainty, but provides increasingly better models that are always open to revision when new data appears. When you accept this, you begin to see that not knowing is not a failure, but a natural part of the learning process. This also relates to how we understand what understanding really means. You can memorize a formula, you can apply it to solve problems, but that does not mean you truly understand the phenomenon. Understanding in a deeper sense is the ability to explain, to connect, to see the relationships between ideas. And that often comes from asking questions, not from accepting answers. When you try to explain something in simple words, you are forced to confront the places where you do not yet understand clearly, and that very process helps you make progress. This is why I have always believed that if you cannot explain something simply, perhaps you do not understand it deeply enough. All of this comes back to one core idea: curiosity. Curiosity is what makes you ask questions in the first place, the drive that keeps you dissatisfied with simple answers, the reason you continue searching even when the problem becomes difficult. Without curiosity, there would be no science, because no one would ask why. When you look at children, you see curiosity in its most primitive form: continuous questions, sometimes without any clear purpose other than understanding the world. Science, to some extent, is the continuation of that spirit, but with more precise tools, with verification methods, and with discipline in thinking. What makes humans special is not that we have all the answers, but that we have the ability to ask increasingly deeper questions and pursue them systematically. When you look back at all the problems we have gone through, from unsolved equations to particles we do not fully understand, to constants we cannot explain, you can see that they are not only challenges, but also opportunities to apply this very philosophy. They force us to be honest about what we know, to doubt our own assumptions, to accept that there are things we do not understand, and to keep our curiosity alive. And if there is one thing I want you to take away, it is the feeling that not having all the answers is not a weakness, but a part of the journey, because it is precisely the unanswered questions that drive science forward. And it is the ability to ask those questions that makes us special. When you return to the original question, the seemingly very simple question of how well we truly understand the universe, you begin to realize that the answer is not a number or a clear conclusion, but a state, a position where we stand between two things. On one side, what we have understood with astonishing accuracy, and on the other, what still lies beyond our reach. We can describe the motion of planets, predict the collision of galaxies, calculate the behavior of fundamental particles with accuracy to many decimal places, and even look back almost to the entire history of the universe, from the first minutes after the Big Bang. But at the same time, we have just gone through a series of problems showing that this picture is not yet complete. We do not yet know how to fully solve the equations describing fluids. We do not understand why gravity is so weak. We do not have a unified theory between quantum mechanics and general relativity. We have not explained the origin of neutrino mass. We do not know where the lithium went. We have never seen a proton decay. We do not fully understand the nature of measurement in quantum mechanics, and we have no answer for why the constants of the universe have the values they do. This may make you feel that we know very little, but if you look at it differently, you will see that what is astonishing is not what we do not know, but what we do know. The fact that we, creatures living on a small planet, orbiting an average star in an ordinary galaxy, can understand the laws governing the entire universe to this extent is itself extraordinary. We have built theories that allow us to predict phenomena we have never observed, and then confirm them through experiment, from gravitational waves to new particles in accelerators. That shows that although our understanding is incomplete, it is not random, but the result of a very specific process, a process based on observation, experimentation, and the willingness to correct ourselves. When you place that next to the gaps we have discussed, you begin to see that science is not a state to be achieved, but an ongoing process, a journey in which every step forward opens up new questions. This leads to a conclusion that may not be comfortable, but is very honest. We do not yet have the final answers, and we may not have them for a long time to come, but that does not make this journey any less valuable. On the contrary, it is exactly what makes it worth pursuing. If every question already had an answer, if there were no more mysteries to explore, then science would no longer be a living process, but merely a list of results. Instead, we are in a position where each new answer does not close the story, but expands it, bringing us closer to a fuller picture, while also showing more clearly what is still missing. And perhaps this is the most important point. Our greatest achievement is not the answers we have found, but the ability to ask the right questions. That ability is not obvious. It requires curiosity, patience, and honesty, and it is what has taken us from simple observations of the sky to complex theories about the structure of reality. When you think about that, you begin to see that understanding a part of the universe is not a failure because we have not understood the whole, but a success because we have come this far. And every piece of understanding we have is not an endpoint, but a foundation for the next step. So when you return to the original question, perhaps the best answer is not how many percent do we understand, but we are continuing to understand more. And it is that process itself that matters. It is a process with no clear endpoint, where each discovery opens up new possibilities, where each question leads to deeper questions. And if you look at it that way, you will see that the incompleteness of our understanding is not a limitation, but an invitation. An invitation to continue exploring, to continue asking questions, to continue looking at the universe with curiosity rather than certainty. It is a feeling of openness, not because we know nothing, but because what we do know shows that there is still so much worth discovering. And perhaps the most beautiful thing about all of this is that we have the ability to participate in that process, the ability to ask questions about the very universe we are a part of, and to pursue those questions as far as we can. That does not guarantee we will find every answer, but it guarantees that we will continue moving forward, step by step, with curiosity as the driving force and uncertainty as an essential part of the journey. If you find that these questions make you think differently about the universe, please hit subscribe so you don't miss the next exploration journeys. See you in the next video, where we will continue to dive deeper into the mysteries that science has not yet been able to solve.